on fundamentals of electrical circuits. Today we discuss several special interconnections of which star delta is also included. Of course, you know the conversion, but let me try to help you by speaking about an easy method. Like for instance, if we want to get the star equivalent from the delta, then as is given in this case, R1 will be given by RB into RC divided by RB plus RC plus RA. That is multiplied by the neighbors and divide by the total. Okay, so this applies to all the branches of the star network. Okay, similarly, if you want to get the delta equivalence from the star, that is, let's say that we want to get RB, then it's the same as equal to R1 plus R3 plus R1 R3, that is the neighbors are multiplied together and divided by the opposite, that is R2. Okay, so this is this is how you can derive the star to delta, delta to star, just from the physical concept of things. Okay, so and this is applicable to this kind of conversion is applicable to resistances, impedances and inductances. For capacitances, it is applicable, but reciprocally. Okay, and if you have only admittances with you, again it is applicable, but the conversion happens to be opposite in nature. Okay, similarly, if we delve deeper, we see that if each of these components are equal, then the star equivalence will be 1/3 the value of the delta components. On the other hand, if we have the components equal in a star structure, then the delta equivalence will be 3 times the resistor, the impedance or the inductance, and 3 times the reciprocal of the capacitance, or C by 3 would be the values of the delta equivalence of a capacitor. Okay, so let's do the problem that we did in symmetry here, and we see that of course we earlier saw that there was a delta right at the middle and of equal values of 1 ohm resistance as is given in the problem, and in that case we see that the star equivalence will be 1/3 the value as was said earlier. So now these 1/3 of ohmic values latch on to the 1 ohms connecting them to the delta, so they are each of values 4/3. So now 4/3 converted to delta will be equal to 4 ohms. Okay, multiply by 3 gives you 4 ohms. So 4 and 1 parallel gives you 1 into 4/5. So these so we have 4/5 between A and B directly, and we have another 4/5, 2 times 4/5 or 8/5 between A, C and B, and so now we have 4/5 and 8/5 giving rise to 2/3 times 4/5 or 8/15 as was assessed earlier. In problem 2 we just examine the utility of conversion in a different, so I'm using it to convey a few concepts as well. Like for instance, in this circuit we see that we have nothing is asked for because it's a different problem altogether. Okay, so we have what is called as a 20 volt source and a 4 amp source feeding a network. So let us look at this central star. We see that we can, from the star we can get a delta such that we get a resistance between 1 and 4 which is the same as equal to 5 plus 10 plus 5 into 10, 50 divided by 10, or in other words 20 ohms. Okay. Similarly, we have a 20 ohm resistor in parallel to the 30 ohm resistor right at the top, and we have a 40 ohm resistor in parallel to the 20 ohms in parallel to the 4 amp source. So this gives rise to quite a lot of simplification of the circuit, because the 20 ohms in parallel with respect to the 20 volt source does not matter at all. It is irrelevant, and you can even discard it for analysis because it has 20 volt across it, and so it will always carry 1 amp. Whatever be the situation, it will be carrying 1 amp. Okay, and so we have a very simple structure where a source is there and a 50 ohm resistor is there, and then we also have a current in parallel with a 40 parallel 20 ohm resistor, which can be converted to a voltage source as the problem demands. Okay, so let's go to other interconnections. So here we have the third problem tells us that a Y network has resistances of 10 ohm each in 2 of its arms. So I've just given a structure such that you need not draw. You can think about it having two arms with 10 ohms, while the third arm has a resistance of 11 ohms in the equivalent delta network. The lowest values in ohms among the three resistances. Okay, so when if you want to get the lowest values, in addition the lowest values should come, and in division the denominator should have the highest value. So it is going to be 10 plus 10 plus 10 into 10 divided by 11, as simple as that. Okay, so let's move on to the fourth problem. So this is just an arithmetic problem, but then the concept of getting a lowest value by adding the smaller values and dividing by the larger values need to be remembered, and also the fact that to get the delta equivalence you have to add the neighbors and then multiply them and subsequently divide by the opposite edge and then add them all together. Okay. So moving on to the fourth problem, we see many currents entering and leaving, and an important concept is that whatever be the network, okay, whatever be the sub-network, all the currents converge to zero, or they all diverge to zero. Or in other words, I suppose this is a very important Kirchhoff's law, and the problem could be of that nature. Okay, so what do we see? Consider the configuration shown in the figure, which is a portion of a large electrical network. Okay, for R equal to 1, whatever be the value of resistances, okay, it does not matter because it's all currents. Okay, it's all a matter of currents. Okay, for R equal to 1 and currents I1 is equal to 2 amps. So we see I1 2 amps. It has been marked there. It's in your mind, you can mark it. And then I4 is equal to minus 1 amps, which means a current 1 ampere is leaving. So now if 1 amps leaves from 2 amps, another 1 amp has to move upward. Okay, as I2. So and then it's given as I5 is equal to minus 4 amps, which means again that 4 amps is leaving. So only 1 amps have been contributed. So another 3 amps will have to flow as I3 or minus I3, and then to make up for the 4 amps that is leaving. Okay, so which of the following is true? Okay, so what is the first answer? It says that I6 is equal to 5 amps. Of course, with 3 amps and 2 amps leaving, I6 will have to be 5 amps. Okay. From this edge, because 2 amps and 3 amps are leaving, it has to total to 5 amps delivering to the network. Okay, so now we need not look at the subsequent answers, but you can definitely see that B is wrong because I3 is mentioned as minus 4 amps, which is not true. Similarly, data is sufficient to conclude that the supposed currents are impossible, which is impossible. Data is insufficient. Of course, data is sufficient, okay, for this case. So moving on to the fifth problem, the two electrical subnetworks, again a subnetwork problem, N1 and N2 are connected through the three resistors as shown in the figure. The voltage across 5 ohm resistor and 1 ohm resistor are given 10 volt and as 10 volt and 5 volt respectively. The voltage across the 15 ohm resistor is what? Okay, so it's very simple in the sense that again the concepts of electrical circuits are important. We see that the 10 volt across 5 ohms means 2 amps entering at the positive terminal, and 5 volt across the 1 ohm resistor means 5 amps entering at the positive terminal. So together 7 amps needs to go out from network N2 back to network N1, which is the balancing act with respect to networks. So if 7 amps enters at the left at the right part of it, then it creates what is called as 7 into 15 105 volts. But 105 volts is negative with respect to whatever was shown in the upper and the lower arms connecting the two networks. Okay, so I suppose this is also very clear, and a similar problem was again repeated for gate examination, which gave two sub networks N1 and N2 connected through a 3 ohm, a 2 ohm and another source. Okay, so which is very similar. Okay, so what is asked is what is the power delivered in watts by the 5 volt source. Okay, so conservation tells us that whatever is created is consumed there itself, and so whatever power is consumed, whatever power is demanded by the two ohmic values are now delivered by this. Okay, so let's look at it in a roundabout manner. We see that the 6 volt across 3 ohms demands 2 amps in the direction such that it enters the positive terminal. Similarly, 2 volt across 2 ohms demands a current of 1 amps entering the positive terminal, which means that only 1 amps will flow, and it will flow in the direction as shown, such that both the 1 amps join together to flow as 2 amps over in the top edge of the top edge connecting the two networks. Okay, so if current flows in the direction which is shown here, it is very clear that it is very clear that that current the current direction and the voltage directions are the same. Okay, so if they are the same, then it is delivering power. If they are opposite to each other, then that element is absorbing power. This is a very important concept that we need to remember. That is, if the current and voltages have the currents and voltages have the same direction, then that element, whatever be the element, it delivers power. On the other hand, if they are oppositely directed, then it absorbs power. So obviously it is delivering power, and it's given by 5 volt into 1 amps, which is 5 watt. Okay, and so now moving on to the 7th problem, which is a similar concept, which tells us again about a sub network with only sources. Okay, and 10 amps flows through the 100 volt source, and they are oppositely directed, so which means that it is absorbing power, and 8 amps flows through the 80 volt source, but they are similarly directed, both the voltage and the current. I suppose we know that the voltage direction is from the negative terminal to the positive terminal. So that means 640 watts is being delivered, unlike in the earlier case, which was 1000 watts being absorbed. And then since 10 amps enters and 8 amps leaves, 2 amps flows downward, and so they follow the same direction. So it is also absorbing 15 into 2, 30 watts. Okay, so what is the question? What is the total power absorbed in the circuit? So it is 1000 minus the rest, as given by 1000 minus 640 plus 30, which is equal to 330 watts. Okay, very simple. Okay, moving on to the 8th problem, which is also very simple, which shows that two networks are hanging together with respect to one single element of 10 ohms. Okay, so this shows this drives in a very important concept of circuits. In circuits, if a current exits, it has to return. Okay, well, that is the meaning of circuit. Right? That is, it follows a full circuit. So it has to go and then it has to return. If there's no return path, then no currents flow. So even without asking, we realize that these circuits are independent with respect to each other. They are almost isolated, but they have the same potential on either edges. That's all that's there. So we have what is called as so no current flow as I. Okay, let's read the problem. Consider circuit shown in the figure. The current I flowing through the 10 ohm resistor is 0. Okay, no doubt about it. Okay, we need not even consider what is happening in the two sub networks connected together through a 10 ohms with no relevance other than making them at the same potential. So we move on to the 9th problem. Here we have okay, just as we had earlier, we have a structure of voltages connected together, voltage sources connected together, and the problem is, in the circuit of figure, the value of the voltage source E is equal to. Okay, so you have to always, in any kind of problem, you have always got to go to the point where maximum information is available. In this case, maximum information is available in the sense on the right side, that is, we have a 0 volt at one edge and 10 volt at the other end. So you have to add together the voltages going from 0 to 10 volt. Okay, so we have, so from 0 there's a reduction of voltage because it's from positive terminal to negative terminal. So we have minus 1 volt, again positive terminal to minus terminal. So we have negative terminal. So we have again minus E. So minus 1 minus E, and then again minus 5 equating to 10. Okay, so altogether you see that E is going to be negative and equal to and it's going to be equal to 15 volt. Okay, so moving to 10th problem. Okay, so here we have a network, and what is asked is what is the current what is the source current. So this is a very important concept. What is the source current? Okay, source current will tell us that. So let's see. So the current I4 in the circuit of figure is equal to. Okay, so this is the source current. Okay, so if you have to have the source current, please remember that the current through the entire branch, okay, where the source X is the same. Okay, so it is so we have to go to the edge A, because that is where the source, where the currents are diverging, and there we have 5 amps and 7 amps going out. So which means that the current is entering there as 12 amps. So, or in other words, I4 is equal to minus 12 amps. Okay, so as simple as that. So all these problems are very simple. Okay, so let's go to the 11th problem, wherein we have an interconnection of sources again, and what is given is, in the interconnection of ideal sources shown in the figure, it is known that 60 volt source is absorbing power. So if it has to absorb power, then the current direction has to be shown as is shown in red here. Okay, so if that is the case, then 12 amps goes through the 20 volt source and delivers a little part of it, and then the rest flows down as source number I. Okay, so everything is fixed. Okay, so what flows in the left hand branch, the left side of the circuit, is going to be I, and on the right side it's going to be 12 amps, and the difference is going to flow through 60 volt to make it as a power absorbing kind of source. Okay, so it's like a battery which is being charged. Okay, so which of the following? So definitely I has to be smaller than 12, because a part of it goes through the 60 volt source. Okay, so there's only one answer which is lesser than 12, and that's going to be 10 amps. Okay, so it's a very simple circuit. So now we move on to problem number 12. Okay, so problem number 12, as can be seen, is a network with many resistances, and what is asked is the equivalent resistance between the terminals A and B is. Okay, so when you are supposed to find out the resistance between terminals at one end, you start the assessment from the other end. Okay, so meanwhile, if there is any simplification, you have to go ahead with that as well. So there is no Wheatstone bridge as such because of the differing values. So, but at the same time, the points marked A and A are connected through a short circuit, or in other words, it's a point, or it can be considered as a stretched point. Okay, so the elements of 6 ohms and 3 ohms can now slide along this line and attach themselves as parallel to 3 ohms on the left side and 6 ohms on the right side, constituting a togetherness of 3 and 6 in parallel, or 2 ohms. Okay, so now we are ready to start from the other end. So 1 and 1 ohms together makes 2 in parallel with the 2 that has been recently constructed is 1 ohms. 1 plus 2 gives you 3 ohms, and this 3 ohms is now in parallel with the originally constructed 2 ohms. So that is 3 to the 6 by 5, 1.2 ohms. So 1.2 ohms added to 0.8 and 1 ohms gives rise to 3 ohms as the effective resistance when looked at from AB terminals. So that's easy. Moving on to 13th problem, which has one source, DC source 2 amps, and all the elements. There's a resistor, inductor, and a capacitor. Okay, and the values are given there for all of them. Okay, so let's read the problem. A segment of a circuit is shown in figure. VR is given as 5 volts, and it's a DC voltage, and it's a resistive content, resistive component. Okay, so there are two DC components. One is the 2 amp source, and another is the voltage across the 5 ohm resistor. So these are the two DC contents, and the others, let's see. VC has a voltage as equal to 4 sine 2t. Okay, so that's the only dynamic component or time dependent component there, and what is asked is the voltage VL. Okay, so VL, now the inductor and the capacitor are the only elements which are dependent upon the change of time for creating a current or a voltage. For instance, for the capacitor, the current through it is given by C dV by dt, and the voltage across the inductor is given by L di by dt. Okay, but at the same time, the DC currents make no inroads or do not make no changes in either of the two circuit elements, that is the inductor and the capacitor. So you can simply discard them. That is, the 2 amp source is removed, and the resistor 5 ohm resistor through which a current flows and creates a DC voltage of 5 volt is also removed. So we have only 2 circuits charging and discharging in tandem. That is the capacitor releases a current which is absorbed by the inductor to create a voltage across it. So what's the current released? C, which is 1 into dV by dt, which is 8 cos 2t. Okay, and now this 8 cos 2t flows through the inductor, and we have L di by dt minus L di by dt, so the negative gets cancelled, and so we have 8 into that is 2 Henry, so 2 into 8 into 2 created out of the differential. So we have 32 sin t back as one of the answers, and it is marked here. Okay. Moving on to the 14th problem. It looks complex, and whenever a complex problem is there, there will be ample methods to solve it, ample scope for solving it. Okay, so let's see. A network of resistors are given, 3 sources are there, but there is maximum information given in the question itself, where it says that if VA minus VB, which means that A is at a higher potential and it's equal to 6 volt with respect to B, okay, then VC minus VD is what? Okay, so very clearly the current is flowing through AB such that a voltage of 6 volt is created, and that current is equal to 3 amps. It's coming from A to B. Okay, and when it goes to B and to the sub circuits on the right side, whatever that happens to it on the other side, it returns. Okay, because only 2 connections are there, one going into sub circuit on the right side and one coming back. So through the from at point D, this current returns, this 3 amps returns in its entirety. This is the only concept in this problem. That is 3 amps goes there and 3 amps returns, and when 3 amps returns there, the 2 amps join with it, and then together they flow through the 1 ohm resistor, causing a voltage drop here where the right side is positive, and so VCD, where C has to be positive, is called as equal to 5 amps into 1 5 volt minus 5 volt. Okay, as simple as that. Now let's move on to an interesting problem here, wherein you can piece together pieces and you can get a very simple solution, which is actually demanded in gate context, in examinations like in the gate context, because a lot of intelligence or observation needs to be put together rather than computational skills. Okay, so let's move to the problem. I hope you notice that there is a 10 volt source powering a circuit which also has a 1 ampere and a 2 ampere DC sources. As I said earlier, first look at the structure of the network and then go on to compartmentalizing. So we have done that, and we see 4 1 ohms. Okay, all of them connected one after another, with of course some divergence, etc. Okay, and a glance at the answer tells us that there is a 0 watt, 5 watt, 10 watt and 100 watt. 0 is always attractive. Okay, so let's look at the problem. The circuit shown, the power supplied by the voltage sources. Can it be 0? That should be the first question that can be asked by in a gate context. If it is 0, it means that both the 2 amps and 1 amps come together, converge through the 1 ohm immediately after it, and then they flow together into the circuit on the left. Okay, so we have 3 into 1 ohms and 1 ohms, 6 volts created there to balance the 10 volt, and then 1 amps flows back into the circuit, and so thereafter there's only 1 amp flowing through the bottom 2 1 ohms, creating another 1 into 2 volts. So we have 1 amp flows back, and so we have 2 amps flowing in and creating a 4 volt drop. Okay, so we have 6 volt at the top and 4 volt at the bottom, balancing together 10 volts. So nothing is demanded out of the 10 volt source, other than the fact that the upper potential has to be 10 volt with respect to the lower point potential. That's all that the 10 volt source does. It does not supply any power. I suppose this is one way of doing the problem. Is what I'm trying to bring to your mind. As also in the in this problem, that is the 16th one. This is the final one in this session. So we have on one side we have 10 volt, and on the other side we have 12 volt and 2 volt in the same direction. I hope you are looking at the external part of the circuit, or the boundary part of the circuit. So we see that there is 14 volt on one side and only 10 volt. So the remaining 4 volt has to come, as per Kirchhoff's voltage, of course, has to come across the 2 ohm resistor there. So if it is 4 volt and that too in the direction as is shown, then it has to carry 2 amps. So 2 amps is the current that is flowing through the uppermost branch as such. Okay, if that is the case, then we'll go a little to the interior. And this is another pattern of solving the problem that I always suggest. You go to the exterior, and from the exterior you slowly move inward. Okay, so then we see that the two ends of the circuit, that is at the two end at the upper tip of the voltage sources, we have a total voltage difference of 2 volt, which is clear from the upper branch as well. So it is 2 volt, and the higher voltage has to be at the 12 volt source. So if that is the case, then why not think in terms of having that 2 volt differential across the 4 ohm and 6 ohm. If that is the case, then of course 6 minus 4 is 2. So the 2 ampere source releases 1 amps to the left side and 1 amps to the right side, creating a 6 volt with the direction as shown, and 4 volt on the other side, making the 12 volt source have a higher voltage with respect to the 10 volt source of 2 volts. Okay, so everything is now more or less correct. So let's see. So in the top branch we have 2 amps. In the 4 ohm we have 1 amps flowing in this direction, and so it contributes to 1 amps for the 2 ohm resistor. The rest has to come from the 12 volt source. So this 1 amp flowing there, and if 2 amp source has to be constructed out of the currents that is converging there. So if 1 amp is flowing outward, 2 amps is also flowing outward, so 3 amps has to come here, and this 3 amps is flowing through the 10 volt source. Okay, moreover, 1 amps also comes from the 6 ohm side, and 2 ampere also comes from the 2 ohm side, and they converge to form what is called as the 3 amps, which is flowing in the 10 volt source. So everything is fitting together, and this is another pattern of doing the problem. So today we can consolidate by saying that we have different network structures wherein all the concepts are more or less the same. That is, if a current is in a branch, it continues all through. Okay, well, it can be a current source or it can be a simple current, as we have seen. Okay, if there is a resistor or an impedance connected directly across a voltage source, that impedance can be removed from consideration, and any impedance in the circuit in the path of the current source can also be removed from consideration, because it adds nothing to analysis. Okay. Similarly, you can fit together some of the already given facts, and you can do the problem in a much better manner, provided you have a glance at the answers, and some of the interesting answers always work out to be more correct with respect to gate examinations. So I suppose for now it's enough, and we'll continue with the remaining sessions in the next session.